Hi, my name is Abhishek Singh Kushwaha. I am a master candidate at Florida Atlantic University, and today I will be presenting my paper titled An Overview of Query Optimization in Relational Systems. This is the outline for this today's presentation. Talking about the motivation, the optimization of SQL queries within a relational database system has been a subject of extensive research since the early 1970s. However, because this field is so large, it is challenging to cover everything in this presentation. Therefore, this presentation will primarily focus on SQL query optimization, offering a selective and condensed perspective on the subject matters. The relational database system offers a declarative interface for accessing stored data, with SQL becoming most widely used query language. Within SQL database system, the query evaluation component has two principal elements: the query execution engine and the query optimizer. The query execution engine implements a range of physical operators which manipulate data streams to generate desired outcomes. Examples of such operators include sorting, sequential scanning, index scanning, nested loop joins, and sort merge joins. These operators serve as a physical fundamental blocks for executing SQL queries. Their execution is represented as a physical operator tree as shown on the right side of the presentation. The query execution engine is also responsible for executing this plan to generate query result. The query optimizer task is to generate an efficient execution plan from a wide range of possible plans for a given SQL query. This task is very complicated because there are many ways to arrange the steps. The speed can change a lot, and picking the right plan is really important for making things run smoothly. For the operator tree, we can write various versions of the algebraic representation. So this is one of the example as shown below. The problem is clearly discussed in the research paper is query optimization in relational database system, particularly focusing on SQL queries. Query optimization involves generating an efficient execution plan for a given SQL query from a space of possible execution plans. The task is not easy because of the following challenges: the large search space, variability in performance, complexity of optimization, and requirements for a good optimizer. Hence, query optimization can be viewed as a challenging search problem. In order to solve this problem, we need a plan and a cost estimation technique and an enumeration algorithm, which will be discussed in the later part of this video. Now, talking about the related work, the System R Optimizer is an innovative project that significantly advanced the field of query optimization in relational database system. The System R Optimizer introduced important ideas and techniques that are still used in modern commercial optimizers today. In this presentation, we are focusing on some key concepts related to select project join queries, which are type of queries often studied in database theory. The System R Optimizer search space explores various sequence of join operation for select project join queries represented by operators trees, which is shown on the right side of the presentation. And this sequence make use of associative and commutative properties of joins, providing flexibility in optimization. And operators include nested loop or sort merge joins, which scan nodes using index or sequential scan. The cost model plays a crucial role in estimating the cost of partial or complete plans, considering factors such as statistics on relation and indexes, selectivity of predicates, CPU, and input-output operation cost. It computes output data stream size, tuple ordering, and execute cost for each operator. One of the key techniques employed by the system or optimizer is dynamic programming, which optimizes query plans by recursively considering subqueries and extending optimal plans, significantly reduces enumeration from O of n factorial to big O of n of 2 power n minus 1 plans. For example, optimal plan for a subquery of size k plus 1 obtained by extending plans for subqueries of size k. Moreover, interesting orders is crucial for eliminating less effective plans. These orders highlight tuple arrangement that can affect following join operation, resulting in more efficient query plans. But there are some limitations in system-R approach. Although system-R optimizer is elegant and influential, it has limitations in extending to include other logical transformations besides join ordering. However, its utilization of cost-based optimization, dynamic programming, and interesting orders has greatly influenced later advancement in optimization architecture. Now talking about the contribution by the author. In search space, query optimization involves exploring a vast search space of possible execution plans for a given SQL query. The search space for a query optimization depends on algebraic transformation that preserve equivalence and the supported physical operators in the system. Different representation of queries such as sparse trees, operator trees, and query graphs are utilized during optimization to explore various execution plans. And the communicating between the operators is done in three ways. Generalizing join sequence involves considering nonlinear join sequence known as bushy join trees, which is shown on the right side of the presentation, and the algebraic expression for this bushy tree is shown below, which can offer potential cost savings but significantly expand the search space. And in outer join and join, techniques for reordering can reduce evaluation cost, optimizing query performance. In group by and join, transformation enable group by operators to precede join, reducing the number of tuples and potentially lowering cost. Stage aggregation techniques further optimize. In reducing multi-block queries to single blocks, merging views allows for the transformation of multiple block queries into single block queries, improving efficiency. However, unfolding becomes complex when views contain select distinct or group by operators. Techniques for merging nested queries involve flattening correlated nested queries into single queries. Uncorrelated nested subqueries can be evaluated only once, optimizing performance. Here is one such example. The above one is a nested query, and when it is flattened into a single query, it is shown like this. Using semi-join like techniques for optimizing multi-block queries, the goal is to reduce redundant computation and ensure relevance between different parts of the query. Conceptually similar to semi-join propagation, but within the context of a single query, transmission cost is not a concern. For example, a query involving the calculation of average salary for each department, which is shown in the first part of the example. Views and table expression are introduced to restrict the computation and improve efficiency, which is shown on the second part of the example. And reformulated query utilizes these views to optimize computation and produce desired error, which is shown on the last part of the presentation. Now talking about the cost estimation, which is a technique required to handle the challenges. In query optimization, accurately estimating the cost of executing a query is essential, This involves evaluating various algebraic expressions and implementation strategies to determine the most resource efficient approach. This process is crucial as it directly impacts the effectiveness of query optimization. The basic cost estimation framework is derived from the system R approach. First, we collect the statistical summaries of the data that has been stored for understanding the statistical properties of the base data and estimating the statistical parameters. And after that, given an operator and the statistical summary from the first step for each of its input data streams, now we determine the statistical summary of the output data stream. Statistical parameters include the number of tuples, physical pages used, and distribution of values on columns, and estimating the cost for executing the operations. Cost estimation determines the cost of an operation considering CPU input-output operations and communication cost. The third technique to resolve the challenges is enumeration algorithm. Enumeration algorithm is essential in query optimization for selecting efficient execution plans. Recent optimization architecture like Starburst and Volcano or Cascades aim for adaptability and efficiency in exploring the search space. In Starburst, employs a query graph model for structural representation of SQL queries. Query rewrite phase transform query graph model using rules in a forward chaining rule engine. Cost information is lacking during rewrite because leading to historic based decisions. In plan optimization phase, physical operators LOLE-POPs are combined in different ways to form higher level operators. Physical operators combination expressed using a grammar-like language, pruning plans with higher cost. Physical operators and cost are propagated bottom-up, similar to system or bottom-up enumeration scheme. In Volcano Cascades, it uses two rules: universal rule-based approach and goal-driven rule application. Volcano and Cascades architecture utilizes rules universally to represent knowledge of the search space. Transformations rules may map algebraic expressions, while implementing rules map expression to operator trees. Dynamic programming is used in a top-down manner for efficiency, leveraging past optimization tasks. In goal-driven rule application, instead of distinct optimization phases, all transformation in Volcano or Cascades are algebraic and cost-based. Mapping from algebraic to physical operators occurs in a single step. Goal-driven application rules determine the next move considering cost. These are some more advanced issues in database query optimization. First one is the distributed database. It deals with the challenges of moving data between different locations, which add extra time and effort to finding the best way to process queries. Over time, the focus shifted from reducing communication cost to make each location handle its data more efficiently. This led to the rise of parallel databases that uses multiple processes to speed up query processing. In parallel database, speed up query response by using several processes to work on tasks simultaneously. They organize data across different processors and allow operations to be carried out independently or in sequence. But this can create issues with how these processors communicate and schedule tasks. In materialized views, the optimization challenges are reformulating queries to utilize materialized views, which can be difficult due to complex conditions and situations where it is hard to determine best approach. Using a two-step optimization process might make optimization more costly, but this can manage by simultaneously exploring different possibilities and generating expressions. These are some other optimization issues. Um, Delaying the creation of plans until runtime information becomes available, taking into account memory usage and other resources constraints when deciding on a plan, adapting optimizer technology to work efficiently in object-oriented system and dealing with ambiguous queries in multimedia and web environments, putting more focus on decision support systems by extending SQL capabilities to enhance optimization. In validation, the validation methodology may involve practical evaluation using benchmark datasets and queries to assess the effectiveness of optimization techniques. Additionally, comparison with the existing approaches and performance analysis on real-world database systems can validate the proposed methodologies and their impact on query performance. The conclusion from this study here are query optimization extend beyond transformation and equivalence. It also required developing a complex infrastructure. Despite many efforts, significant challenges remain unsolved, highlighting the importance of understanding the existing engineering framework for making impactful contribution to query optimization. That's it for this presentation. I hope you enjoyed it.